All right, let's go ahead and get started. So thank you again, everybody who is joining us for today's webinar, What's New in Kubernetes 1.14. I'm Caitlin Barnard on the communications team for the release, and I'm going to be helping moderate and run the slides for today's webinar. I'd also like to welcome our other presenters today. We've got Laurence, the 1.14 Enhancements Lead, who will be going over some of the major features in this release. We're also joined by Michelle Au of SIG-Storage, who's going to be discussing persistent local volumes, one of our GA features of this release. And then from SIG-Windows, we have Michael and Patrick Lang, who are going to be talking about production level support for our Windows nodes. And as I just referenced, this will be our agenda. Just a few housekeeping items before we get started. As an attendee, you are not able to speak. So if you have any questions during the webinar, there's a Q&A box at the bottom of your screen. Feel free to use that. Drop your questions in there, and then we'll get to as many questions as we can at the end of the webinar. Just a reminder that the session is being recorded and will be sent out along with the slides later today. So with that, I'm going to hand it over to Claire to talk a little bit about the features of this release.
Great, thanks, Caitlin. So to give an overview of some of the enhancements that came in 1.14, we saw 31 total enhancements that were tracked during the 1.14 cycle. 10 of those enhancements were stable, and it's worth noting that 1.14 saw the most number of stable enhancements in a Kubernetes release to date. We also had 12 that were graduating to beta, and then we had 9 introduced as alpha features. And I'm excited to share a couple of the stable enhancements and one of the beta ones in the highlight section. So first up, we've got the updated plugin mechanism for kubectl. In addition to this exciting new enhancement, it's also worth noting that kubectl got a new logo and new docs in the 1.14 cycle. But this enhancement specifically, it is building on the theme of extensibility that we've seen in the past few Kubernetes releases. So it's helping to extend some of the functionality of kubectl by allowing users to create and publish their own kubectl subcommands. And we can go to the next slide, Caitlin. And another additional kubectl related enhancement is integrating customize into kubectl. So again, helping with some more user-friendly extensible features, we now have customize, which will introduce declarative workflows for users to access kubectl commands. This will help with many longstanding issues that users have been facing. And so it's really exciting to see both of these two features go GA for kubectl. And then next, all right, we have pod readiness gate, another enhancement that builds on the theme of extensibility. Pod readiness gates are allowing external feedback to be injected into pod status to help users understand when their pods are ready to serve traffic. These additional indicators can help limit service disruption and any other reasons why your pods could go down if they weren't ready to serve traffic. Next, we have PID limiting. So this new feature will allow process IDs, also known as PIDs, to have more isolation. So we have pod to pod isolation and node to pod isolation, and this will help prevent PID exhaustion. Hitting PID resource targets is a fairly easy thing to do, and doing so can often lead to instability. So having this feature or this enhancement will ensure that PIDs have a limited impact to other workloads. Next, we've got adding in pod priority and preemption. another feature, again, building on extensibility here in Kubernetes 1.14. This is enabling users to set pod priority relative to other pods. So indicating what pods are higher priority and should be scheduled ahead of lower priority pods. And this will also enable, or this will also help if you run out of resources, making sure that lower priority pods are removed to allow for higher priority pods to run. And the last feature we wanted to call, or the last enhancement added that we want to call out as a highlight, is hardening the default RBAC discovery cluster bindings. This enhancement was in response to a CVE that came out late in November. A few of you might be familiar with it, 2018-100-2105. And this is building on the security posture for Kubernetes by removing the discovery from the set of APIs which allow unauthenticated access by default. So another great enhancement to bring in to help improve overall security posture for folks using Kubernetes. And with that, I would like to pass it off to Michelle, who's going to go more deep into details with persistent local volumes.
All right, thanks, Claire. Yeah, my name is Michelle. I am a member of SIG-Storage, and I was the primary lead for the local persistent volumes feature. Next slide. So to give an overview of the feature, what it does is it lets you specify direct attached disks as a persistent volume, and then you can use them in your pods with the same persistent volume claim interface that you already use for persistent volumes in Kubernetes. So as simple as this sounds, this was actually not really easy to do before we implemented this feature. Kubernetes previously mainly supported remote storage systems like a cloud provider's remote block storage service, or networked file systems like NFS. And as a result of that, many of the Kubernetes components assumed that storage is equally accessible from any node in the cluster. So if before we had this feature, if users actually wanted to use local disks, they would have to manually track and manage the local disks themselves and manually schedule their pods to specific nodes. And in some cases, they would have to write custom schedulers for their application that had to do this, environment-specific disk management. So as part of this feature, we really wanted to simplify that use case and make it easier for users to be able to use these disks and have first-class knowledge of local disks in the Kubernetes components. So one of the big features that we added was to add extra intelligence into the Kubernetes scheduler so that it could recognize that some persistent volumes may actually not be globally accessible and are actually restricted to specific nodes in the cluster. So now, if you use a local volume in your pod, it will always be scheduled to the node where that disk is located on. And when we're initially choosing a persistent volume for your claim, we will take into account what nodes have available local volumes, and we'll also consider any other scheduling constraints that your pod might have, such as CPU or memory requirements, node selectors, pod affinity or anti-affinity, and so on. So by adding first-class support for this feature into the core scheduler, we've eliminated the need for users to write custom schedulers, and it can also easily integrate with any other future feature added to the core scheduler. So in terms of the application workloads that we're targeting for this feature, our primary use case is high performance distributed databases that are deployed using stateful sets or an operator. These workloads can benefit from getting direct access to local disks in order to get higher performance and lower cost. But there are trade-offs of lower availability and no redundancy at the storage layer. Next slide. So that brings me to the caveats of this feature. Local persistent volumes is not designed to be a general purpose storage solution. There are definitely many trade-offs that you need to consider if you want to use this feature. The biggest trade-off, in my opinion, is that your pod becomes inflexible with respect to scheduling. In turn, that makes it more prone to data unavailability and even data loss. Once your pod uses a local volume, it's bound to that node forever, and it can only be scheduled to that node. So if that node or disk fails, then your pod is also stuck since it's bound to the volume that's bound to the node. So to deal with this, at your application layer, you will need to implement data redundancy and also have a frequent backup plan to store your critical data in a more reliable storage backend. In addition, you'll need to put into place good monitoring and alerting processes so that you can be notified of any of these failure conditions. And if you want to automate the recovery process, you may also need to build those steps into an operator. One more aspect that you need to pay careful attention to are node upgrades. You have to make sure that which nodes you upgrade are carefully ordered and coordinated so that you don't end up bringing your application below quorum. And especially in cloud environments where local disks are not actually persistent, you will need to migrate or replicate your data to the new nodes. If you're also planning on running the workloads that use local volumes with other workloads in your cluster, I would also recommend that you use the pod priority and preemption feature, which also went GA in 1.14. This allows you to give your pods that use local volumes a higher priority so that lower priority pods can be kicked out to make room for them. And in addition, other notable Kubernetes features such as dynamic provisioning and node autoscaling are not integrated with local persistent volumes either, which means that you'll have to do some more capacity planning and allocation, especially if you're in an on-premise environment. So definitely there are quite a few major trade-offs with this feature, and for that reason, local persistent volumes are not a general purpose solution that you can apply to all your applications. They're really best suited for those workloads that already handle data redundancy at the application layer and can tolerate data unavailability and loss. Also, given all the extra steps needed for capacity allocation and failure recovery, I've seen that the most successful users of this feature end up using it for large-scale data services that already has a dedicated ops team that's able to manage and support it. Next slide. Now, that being said, interest and adoption of this feature has been very strong since the beginning when we first designed this 2 years ago. We got a lot of great alpha and beta testers who actually use the feature in production, both in cloud environments and also on-premise environments and at large scale. In some cases, I've seen people use the feature with clusters over 1,000 nodes and over 10,000 local persistent volumes. So being able to run at this scale definitely helped uncover many race conditions that we had in the scheduler. We even had to redesign part of the feature at some point to be able to handle this scale. But I'm really glad to say that after all of this, all of our scale testing and beta testers, we really have the confidence to promote this feature to GA in 1.14. All right, next slide. So now I want to shift topics a little bit and talk about how you can actually use this feature from a perspective of a Kubernetes user. This part is really simple. It uses the same persistent volume claim interface that you already use for remote persistent volume types in Kubernetes. The only difference here is that you need to specify a different storage class that you've defined to represent your local disks. This API gives you application portability. You can take the same application pod spec and the persistent volume claim spec and deploy it on another cluster or another environment. You can easily swap out the storage class to try out multiple storage backends. Or if you have a multi-cluster management layer, your cluster admin can provide storage classes all with the same name so that you can even just use the same exact persistent volume claim with the same storage class across all your different clusters and environments. So our main goal with respect to the user interface is to try to keep it as simple and familiar as possible so that we can give this portable and consistent API experience. So all the actual magic of the feature in the scheduler and in the storage layer actually happens below the user APIs. So if we go on to the next slide. Here in our admin APIs, this is where we can start providing that storage provider specific and environment specific details. So as a Kubernetes admin, what you would do is to create a storage class and also enable the intelligent scheduling logic that we've built in. This is what the volume binding mode wait for first consumer setting does. It tells Kubernetes that the initial volume binding of a persistent volume claim should be processed by the scheduler. And it should also wait until there's a pod that actually needs to use it. All right, next slide. So that's enabling the storage class. And now moving on, we have to deal with creation of the persistent volume objects themselves. This is probably the most complicated part of the feature. And this is something that the cluster administrator needs to handle before applications can start using the local persistent volumes. So like I said earlier, dynamic provisioning is not supported at the moment. So disk allocation and management is more involved with local volumes than most other cloud storage solutions that sort of just work out of the box. For local volumes, you kind of need to be your own cloud provider. That being said, we've tried to develop some tools and external controllers that can help automate some of this process. So I have a diagram here of a typical life cycle of a local disk when you're using it with this feature. First, it is made available to Kubernetes. Once that's available, then Kubernetes workloads can consume it through the persistent volume claims. And then when the workload is done with that volume and doesn't need it anymore, it releases it. And then we end up cleaning up that disk and putting it back into the Kubernetes pool. Next slide. Going into some more detail, let's start with how to make the disk available to Kubernetes. This step really depends on your environment and what workloads you want to support. Depending on your workload requirements, you may want to do things like partition the disks or RAID the disks. Some providers like GKE may already automate some of these steps for you. But if you are sort of managing Kubernetes on your own, then this is definitely easier to automate if you can make your machine types and your local disk layouts fixed and well-defined without too many variations between machine types. So once you determine how you want to prepare the disks, then you need to link them into a dedicated directory for every storage class you want to offer in your cluster. Next slide. So once this is done, then this is where our external controller comes in. We've developed a controller that we've called the local volume static provisioner. It is different. It's very important to note this is different from a dynamic provisioner in that it doesn't actually carve out persistent volumes on demand. Instead, what it does is it collects and manages the inventory of local disks that you've prepared in the previous step, and then pre-create the persistent volume objects for them. So once the disk is made available to the static provisioner, then it handles the rest of the disk and volume management lifecycle from there. Application pods it creates the PVs for every local disk, which then the application pods can request using the persistent volume claims. When the claim ends up being released, then the controller handles cleaning up all the data on that disk, deleting the persistent volume object, and then creating a brand new persistent volume for it. This continues in a cycle until you finally need to decommission the disk and take it out of service. Next slide. Right, so I know that was a lot of information, and you can see that while the feature itself is stable and being run at scale, the setup and recovery handling are still very involved and non-trivial processes. So improving these aspects is the focus of the next phase of the project, and we could definitely use help in this area. We're looking for folks that can take ownership for each of these different tasks, design, and help drive a solution. So if you're interested, please reach out to me or join one of our sig-storage meetings, and we can help point you in the right direction. And if you want even more detail on how to use the feature, check out the blog post and documentation, which has examples and more detailed steps. And again, I'm available via Slack or GitHub to help answer any other questions you may have. Thank you so much for your interest. I'm going to hand it back to Michael and Patrick now to talk about Windows.
Hello, everybody. This is Michael and Patrick. We're the two chairs for SIG-Windows, and we're super excited with the 1.14 release to announce production level support for Windows nodes. Next slide, please. So we'll give you guys a little bit of a history of how Windows got to here. We'll give you a high-level overview of some of the features, and then we'll deep dive into a demo to give you a hands-on experience on how it is to manage Windows within Kubernetes and also be able to publish some Windows applications into Kubernetes. So our journey was fairly long. We started with version 1.5 back in December 2016 with the alpha release. That release basically allowed you to run the kubelet and the kubeproxy on Windows. And it did have a lot of limitations around the features, but it did enable everybody to show the art of the possible and show us what it would look like to have Windows containers in Kubernetes. With version 1.9, exactly a year later in December of 17th, we shipped our beta, where we had a tremendous updates in functionality, both at the networking layer as well as at the compute layer. And then we're here in version 1.14 in March of 2019, where we're allowing you to run production level workloads on Kubernetes with Windows Server 2019. Now, Windows Server 2019 is a requirement for both the Windows nodes in your Kubernetes environment, as well as the containers running within those nodes. That's because Windows Server 2019 is the best release to date for container support. It includes a lot of enhancements, both from a stability, reliability, as well as a rich feature set for the networking and the compute layer that we needed in Kubernetes. Next slide, please. So when we look at Windows containers in Kubernetes, we kind of created 3 buckets here. The first one is compute. We support Windows Server 2019, both for containers as well as for nodes. We support a lot of different workload types, from pods, service, workload controllers, as well as metrics and quotas. So a lot of the features that you're used to using in Kubernetes for Linux containers, you can now use them for Windows. There are, of course, limitations, and we have a very comprehensive documentation on kubernetes.io that you can read to both understand the compute, network, and storage features and see how they compare to Linux and what you can use both from a feature standpoint as well as an API standpoint. Now, going into storage and networking, we're going to give you a little bit of a deep dive into the different CNIs in a second, but we support node port, cluster IP, load balancer, and external name from the networking standpoint. On the storage side, we support flex volume with the SMB and iSCSI out of 3 plugins. And we also have support for Azure Disk, Azure File, as well as the GCE persistent disks. So we got you covered here at the basic layer for the storage subsystem, and we're making additional enhancements with future releases of Kubernetes to introduce more support for storage providers. And on the security side, with Kubernetes 1.14, we shipped a feature called Group Managed Service Accounts in alpha, and that feature allows you to give to your containers and to your pod an identity into your Active Directory. So that's very important in a Windows environment because your application may need to access an external database or a file share that's secured using Active Directory. So with GMSA, you can give an identity to the network and be able to provide the right access control into your file share and your database so that your container running in Kubernetes is the only one that's authorized to access that. We look forward to enhancing the functionality with future releases, and we're going to make it better and better. Next slide, please. And I'll hand it off to Patrick to talk about networking.
Yeah, thanks, Michael. Yeah, so from a networking standpoint, one of our main goals was to make sure that the networking was something that was both consistent with what was used on Linux, but also interoperable. And so there's a number of different networking plugins available. My team happens to work on one called Azure CNI, that's focused on using the IP address management from a cloud provider. But we also work with the popular Flannel plugin that allows traffic routing between pods and between services, both between Linux and Linux, Linux and Windows, Windows and Windows. Like all those combinations work, both using the host gateway routing mode, as well as using VXLAN for overlay. And if you're at all familiar with the OpenStack project, you've probably heard of Open Virtual Switch and then their Open Virtual Networking Controller. Those plugins have been updated as well, so that way, if you're deploying in an OpenStack type environment, then you can have a networking model that's consistent there, and also, interoperable between both Linux and Windows. And the last thing I wanted to mention on this is to make adapting to new environments a little bit easier. There's actually two open source plugins that have been contributed over to the container networking /plugins repo over on GitHub. And what they do is they just focus on programming the Windows network interfaces and routing that's necessary. And so one of those is focused on bridge networking, one of them is focused on overlay networking. What this means is if you're using another plugin for IP address management or policy that doesn't yet have Windows support, they don't necessarily need to do all the hard work to port all of that code to the Windows APIs that are used for creating network interfaces and routes. Instead, they can delegate to one of these plugins that still follows the same CNI interface, but it can do the heavy lifting of being able to create those endpoints and get that stuff configured, so that way the code sitting on top of it can be shared across both Windows and Linux. And so, we've got both, tailored solutions for specific plugins and specific cloud providers, as well as generic solutions available that others can build on top of. Next slide.
Thank you, Patrick. It's worth noting that OVN Kubernetes is the only CNI today that allows you to set up distributed calls via Kubernetes policies. So if that's a requirement for your environment, maybe you should take a look at that first right now. On the what's next for Windows, we got to GA right now and we're stable, but we're not stopping. We have a tremendous amount of customers that are asking us for a variety of things. So we're going to listen to that user feedback. We're going to prioritize and make sure that we address the concerns that fit the biggest part of our customer base. And we're also going to be investing in a few sets of additional capabilities. The first one is kubeadm support. kubeadm is becoming the de facto standard for users to deploy a Kubernetes cluster, and we want to make sure that as you're investing in solutions like kubeadm, you have the ability to both configure and create a Kubernetes cluster that includes Windows nodes. So that work is ongoing, and we're hoping to give you a preview of that work in some alpha or beta release with 1.15. We're also advancing our support for CRI Containerd, which will also include the runtime class implementation for Hyper-V isolation. Hyper-V isolation is going to open up the types of containers that you can run in Windows Server, including the ability to run older versions of the operating system in containers on top of Windows Server 2019. And obviously, Hyper-V isolation gives you enhanced isolation since you're almost running in a lightweight virtual machine. So you're getting isolation from the kernel, you're getting isolation at the networking layer, and in environments where security is super important for your containers, this is going to be the perfect solution for it. Like I mentioned earlier, we're going to continue investing in group managed service accounts, and we're going to promote the feature to beta with 1.15. And we're going to continue working with different storage and networking vendors to advance our networking and storage solutions and introduce more CNIs and storage plugins into our environment for Windows. Now, when you look at where we are and where we started, we've made a tremendous amount of progress. We now allow you to use a consistent same set of tools with Kubernetes to manage both your Windows and your Linux-based applications. And we're going to show you in a demo in a few seconds how you can exactly do that. You don't need to invest in different tools to manage your infrastructure, and Windows-based applications for the first time can be orchestrated in Kubernetes. Go ahead, Patrick.
All right, let me switch over to the screen share here. Okay, did that load up all right? Okay. All right, so the first thing I want to start off with is just showing that we're using the same consistent tools across both Windows and Linux here. So right now I'm SSH'd into one of my nodes that happens to be running the controller manager and things like that. But the same kube control commands are able to return results and show me containers that are running both on the Windows and the Linux nodes as well. And so there's no real difference when it comes to the command line experience here, and that's because the APIs underneath are the same between Linux and Windows. So from this Linux node here, I can see all the pods that are running, including some that are going to be running on Windows. And likewise, if I switch over to my Windows machine here, this is just like a development machine that I have set up, but I get the same consistent experience between kube control as I do on Linux, and so it means that administrators and developers can operate wherever they're most comfortable. So if they want to use Mac, if they want to use Linux, if they want to use Windows, kube control and even tools like Helm are going to be the same no matter where you're running them. So let me get the status of this deployment here, which is actually one of my applications that's running on Windows. And so looking at the results from this Helm chart, it currently has two different deployments. One of them is a SQL Server instance, and one of them is a web service. And then, of course, I've got service endpoints for those to connect. The chart I actually deployed this from is available over on my GitHub profile. But just to show you a couple quick things here, the database is actually running on one of the Linux nodes. If I go back over here to values, we can see that I've actually got this set up running just a SQL Developer Edition. So if I want to do a quick test deployment, or even deploy this as part of like my continuous integration and testing solution, then that may be a good option for me. And then likewise, if I wanted to deploy this in production, I could simply change my chart here and actually have it deployed to a SQL instance that's provided as part of the Kubernetes service catalog. So like all these tools that are part of the Kubernetes ecosystem, are all still there. And if I go and look at my web deployment that's here in the chart, we can see that all the YAML is consistent with Kubernetes. This happens to be a Helm chart, and so you'll see some of these variables in there. But this is going to be deploying a Windows web service, and then it's setting all of the right things that it needs to be able to identify that SQL database as secrets that are going to be available right there in Kubernetes. And so I'm using all the same primitives, deployments, pods, containers, secrets for this Windows deployment. And then so going back here, let's go ahead and take a look at what's running. So external IP. And so now I'm connected to this site, where my application is running. This is an old example that was published a number of years ago as part of a class on writing applications using the .NET framework. And so this code wasn't changed. I just repackaged this up in a container and then adjusted the config so that it would know how to be able to identify that database from that Kubernetes secret, as opposed from being hard-coded in that XML file.
And that's a super important point, Patrick. So one of the powers of this integration that we added Windows into Kubernetes is the fact that you can have a heterogeneous cluster, but more importantly, we give you the ability now to containerize existing .NET applications and existing Windows applications with minimal effort and package them into a container. That way you need to eliminate all hardware or underutilized virtual machines. You can do that, and you can streamline that migration into Kubernetes.
Yes, yeah, absolutely. And since I just accessed that service, I'll show you another quick example here. And so using the same familiar tools, I can actually connect to that pod and open up PowerShell within that running pod. And so this means that Windows admins and developers, once they connect to their pod, can still get that same experience they're used to. And last 20 lines of this log file, what that means that if I've got tools as part of my workflow that I run to be able to troubleshoot applications, or gather logs and things like that, I can still adapt those and use them under Kubernetes. And so, my skills translate both, from Kubernetes on, Linux or Windows, but also because the application is still running on Windows as it is, the developers don't have to, completely learn a new OS in order to, remain productive while still running in Kubernetes. So that was just a quick example of connecting to that pod. And then, the other deployment that I have up and running here, I've got another web service running here, and so also the typical things around scaling, like kube control. So if I want to be able to scale things up or down based as needed, depending on load, all those same primitives that I'm used to in terms of having replica sets, and then all of these are labeled the right way so that my service and my load balancer can connect to those. And so this is all working, exactly the same way I'd expect it to, and it's picking up all the endpoints, for this other application that's running there on Windows. And this is just a real basic website here, but it lets people use the same built-in roles that they've been using, but take advantage of the benefits of containerization as part of the development and deployment workflow. And so if you want to see more about this in detail, I actually did a presentation that's available from KubeCon last year, where I actually walked through this in a lot more details. And so if you want to see more about it, be sure to check out the video or get the slides over here from the past KubeCon site. And of course, all the source for these demos is available over on GitHub. So I think that's all the main stuff I wanted to show.
Thank you, Patrick. I appreciate it. So, and Patrick and I lead SIG-Windows, who have weekly meetings. So if you guys are interested, you can on the Kubernetes website, there's a listing of all the SIGs. You can find our Zoom meeting. You can attend. You can come to our Slack channel and ask us questions or ask for advice. We'd love to have more people to be involved in Windows. Either come help us write docs, find bugs, or even write some features. So thank you all so much.
Yeah, and I see there was a couple of questions that were just dropped on the chat there. So I guess I'll get a couple of those if we're okay on time. The first one was, can you have Windows nodes running some of the master roles? And so some of those components can be built on Windows today, but they're not something that we're currently testing and supporting on Windows itself. If that's something you're looking for, please drop by the SIG-Windows channel or reach out to one of us directly, because we'd love to hear more. It's not something that's a priority, but if there's a particularly good reason to do it, we're looking for the community to tell us, and then we could see about getting that in a future release. And then there was another one, is Windows 2019 support on AKS. So there's two parts to that. We've got an open source project called AKS Engine that can actually deploy customized clusters on Azure. And then there's also a set of scripts that that Yuju Hong has created that work on GCE as well. Both of those will let you build and maintain your own clusters on one of those cloud environments. And so that's what people are typically using today for development purposes. There's also been previews announced, and there are signups available. One of them is for Azure Kubernetes Service, which I happen to work on. So if you get to sign up there, then we'll have people reaching out and offering invites to that preview. And then Dustin Kirkland at Google Next last week also announced, and they've got a sign-up sheet available there. So keep watching that space if you're looking for a preview from your cloud provider, because those are coming soon. There are two questions related to GUI apps, and the focus is on headless server apps running on Windows Server 2019. So this isn't something that you would use to deploy things out to like someone's desktop. There's other solutions available for that from the Microsoft Windows team. If you look up things like the Enterprise Store for Business, rather than using Docker, those have a little converter tool that let you package an application up in deployment. That's not managed by Kubernetes. AWS, unfortunately, I'm not an expert on AWS, so I can't cover that question. Do you happen to know anything about that, Michael?
No, I know they're working on supporting Windows containers and specifically the Kubernetes release, but can't speak to any dates. You'll have to go directly through the public cloud vendor for dates. As we have them, we usually publish them within the Kubernetes community, but no data right now.
I see there was also a question about HPA. I believe Ben's got that working. Do you happen to know the latest on that, Michael?
Yeah, so the horizontal pod autoscaler works. I already answered the question from the Q&A, so they should follow the exact same things as Linux. They'll get so what we've done in the kubelet, we have both metrics, CPU and memory metrics that you'll be able to ingest and define your policy for horizontal pod autoscaling, and it should work the same way on Windows as it does on Linux.
Okay. And then there was another question about AtCD and whether or not a AtCD cluster can span Windows and Linux. Unfortunately, I don't know about that. Is that something you've looked into?
I don't know how well AtCD will run on Windows in this situation. I honestly haven't seen anybody try to deploy it in that way. If someone is willing to give this a shot and come to SIG-Windows Slack channel and discuss with us, we'll be more than happy to explore this with you, but we don't have any data on that right now.
Okay. I see that that Jason also put if you look at the Q&A, Jason also put a link in there saying that there was some info about an AWS preview. So, and yes, you can use CPU and memory resource constraints on pods. If you take a look at that sample repo I have for IIS, that one actually has a CPU limit set on it. I'll try to paste that in the answers so you can see that.
In our documentation, we talk a little bit about some restrictions around CPU and memory and reservations. So if you're interested in exploring more in that path, please go ahead and read the docs in kubernetes.io. There is a section specifically around what happens around reservations and memory.
And also, so yes, the Windows networking team has also been working with Calico, and so Calico is available for doing policies. Unfortunately, I'm not an expert in Calico, but I believe they have a session recorded from, I don't know, I think it was either at Microsoft Build or possibly at KubeCon. But there should be some more details out there if you search for Calico in Windows, because it was announced a while back, and I believe that it's working now. And then another clarification. So for 1.14, we're supporting Windows nodes, and that's running Windows containers. We're not supporting creating a cluster where Windows is running things like the API server, controller and scheduler. Those are still running on Linux today. But if that's something you need, let us know in SIG-Windows, and we'll talk about it.
There is a question around scaling pods based on custom metrics. I don't believe we have anybody that has tried this so far. We'll give this a shot and document that if that works, or if the person that asked that question would like to try it out, let us know. I think the next question is probably for Michelle.
Yes. This is what is the basic difference between host path volumes and local PVs. This is a really great question. One way that I like to think about it is that a host path is completely unmanaged by Kubernetes. So what this means is when you specify a host path, all Kubernetes does is just pass it directly through to your container, and it doesn't do anything with it. Whereas local persistent volumes, you can think of it closer to the other standard block volume types that we have in Kubernetes. So things like FS group management and file system management are supported with local PVs, whereas those operations are not used by host path. And the other major thing is that local persistent volumes are only accessible through the persistent volume interface, so that you cannot directly specify a local path in your pod. This gives much stronger security boundaries, so that your pods cannot just arbitrarily access any file in your cluster.
And that would also make your pod YAML a little more portable too, because it's
Correct.
a dependency on that path existing on the host.
Yeah, correct. What folks have had to do before we had local persistent volumes, basically people had to use host path, and what that meant was that they would have to manually construct their pod spec with the path of the disk on the specific node, and then bind that pod to the specific node. So it was really hard to use in something like stateful sets, and you wouldn't be able to scale up or scale down very easily.
So there's another Windows question about pod-to-pod communication. And yes, that works between Windows nodes, and it works between Windows and Linux nodes.
One caveat there: if you are trying to make sure that your pod is able to communicate with the outside world or even internally to another node or another pod, make sure that you don't use ping. The ICMP protocol is not fully defined for Windows nodes, so use curl. So if you need to ensure that your pod can talk to the outside world and verify your network connectivity, use curl for those commands.
I think we have another question for Windows. Is it possible to use Astia for the pods running on Windows nodes?
I believe there's a team at Microsoft that's working to make sure Envoy works well on Windows. I don't know what their latest status is. They're doing that work in the open source community. I know they're working on it. I don't know if it's done yet.
Yeah, that's the first step towards getting that working.
Eventually, that's a plan that you'll be able to use Istio and Envoy on Windows as well. So if you wanted to create a service mesh, I just don't have any dates from that team yet.
All right, and I think we have another question for Michelle. When a pod is using a host path volume, if the node hosting it fails, a new node can come up and the pod is rescheduled on it. Is it the same or local PV, or do one have to manage failure manually?
So it depends on how you use the host path volume. If you didn't bind your pod using that host path volume to a specific node, then that pod is free to be scheduled to another node. But it really depends on how your workload can manage that, because if you don't bind your pod to a specific node, then it's possible you can have multiple pods scheduled to the same node and sort of clobber each other on the same disk. So one of the things that local PV does is it does bind your pod to the specific node indirectly. You don't actually have to say which node in your pod spec. It's sort of inferred through the persistent volume interface. That way, if a node fails, what will happen to your pod is it will end up in some pending or error state. And then that's when you can have an operator come in and then, assess the situation and see, oh, can I just reschedule to another pod, get a brand new blank disk, and rehydrate all the data from it. If your application can do that, then you can go ahead and delete your PVC, and then the stateful set will go and create a new PVC, and it will get bound to a new node.
Okay, I see there's a question about firewall rules on Windows nodes as well. And so you still leave the firewall enabled on the individual Windows nodes, so that way you can control access the same way you do before. But if you want to set additional rules on how the pods communicate, particularly around like ingress and egress rules, then that's where you would look at a container focused policy engine like Calico, or as Michael mentioned, setting rules within your OVN control plane. And then Arun was asking about Openshift. If you're referring to Openshift with Windows, there is a sign-up form available, and then they're inviting people to that preview as well.
Just FYI, there are sign-up forms also for Google Cloud and GCE for Windows support as well. That was announced at Google Next a couple of weeks ago. So, now that Windows is GA in Kubernetes, you're going to see a lot of the different distributions of Kubernetes, whether from a public cloud provider or on-premise. They're all going to start supporting Windows, and you're going to see signups for alphas, betas, technical previews, or even for GA. So contact the vendor that you're most comfortable with, and I'm sure they're working on this already.
Also, Michelle, there was a question about shared storage provided by Ceph for pods to mount. Is that something that would be used with persistent local volumes, or would you recommend using the existing Ceph provider that's available?
So yeah, there's an existing Ceph volume type. I would highly recommend just using that instead of adding one more layer of redirection through local volumes. What ends up happening is that local volumes is starting to get used as a implementation detail for a lot of these software-defined storage systems. So you'll see things like, potentially Ceph that could, redesign their the way that they manage local disks and instead use local persistent volumes instead. But that would be more of an implementation detail rather than something that's exposed directly to the users.
Caitlin, should we do a last call for questions, or kind of start wrapping it up?
Yeah, we're over here on time, so I'm going to start wrapping us up. Thank you all again for joining us today and for all of the great questions. And thank you so much to our presenters who took the time to dive into all these features today. So just a reminder, the webinar recording and slides will be online later today. And have a great day, everyone.